Welcome back to question 2 of this series where we learn how to calculate the pH of a buffer solution. Question 2 reads, calculate the pH of the buffer that results from mixing 60.0 milliliters of 0.250 molar formic acid and 15.0 milliliters of 0.500 molar of NaCHO2. What we have here is an interesting situation where two solutions are being combined. So originally, the solution containing this chemical had a concentration of 0.250 molar. Of course, after combining it with another solution, that concentration will change. The first thing that I'll do is add up the 60 and the 15. So 60.0 plus 15.0 milliliters gives us 75.0 milliliters. So I need to find the brand new concentration for HCHO2. First, I will reduce it down to how many moles it is originally, and I can do that by converting 60.0 milliliters into liters. 60.0 milliliters into liters is 0.0600. I'll multiply this to the concentration, molars. Remember, molars is moles per liter. So multiply to 0.250 moles per liter, and now I have how many moles. Once you have the amount of moles, you can then divide it by the total volume, which in our case, in liters, is 0.0750 liters. So I'm going to take 0.06, this number, multiply to 0.250, that is equal to 0.015 moles. Divide that now by 0.0750. And that gives us a brand new concentration of 0.200 molars. Notice that it kind of got diluted from 0.25 to 0.2. We have to do the exact same thing, but for this molecule. 0.0150 liters and multiply it to 0.500 moles per liter. This cancels out with that. We're left with moles, and we'll divide that again by 0.0750. This will give us our brand new concentration of NaCHO2. If you plug this all into your calculator correctly, you should end up with 0.100 molar. Just to be clear, this is the new concentration of this solution. That's the concentration, and the new concentration of NaCHO2. Now, just like what we did in question 1, we can now go ahead and find out the pH. We'll first create a balanced chemical equation. So HCHO2 plus liquid water, and that's aqueous. This breaks down into hydronium ions and the ionic version of this molecule, which is plus CHO2 minus, and that's aqueous. Using the concentration of NaCHO2, I'll write down that the initial concentration of this molecule is 0.100, and the concentration of this solution is 0.200 molars. We'll also need to find the change and the equilibrium. We don't really care about the H2O because that's in its liquid state. It's not part of the equilibrium expression. And over here, since this is a weak acid, H3O plus, very little of that is formed. So I'll write down approximately equal to 0. To find the equilibrium expression, we'll set one of these molecules as X. So I'll set this as X, and make sure that this chemical equation is in fact balanced. It is balanced, so that's a good thing. Comparing stoichiometrically the numbers in front, we have a 1-to-1 ratio, so this is negative X, and this is also negative X. If you're curious about why it's negative, it's because we're comparing reactants with products. Anytime you do that, you end up with the opposite sign. I'll add these up to find E. Remember, I plus C is equal to E. So 0.200 plus X, and over here, negative X, and over here, 0.100 minus X. Next, we'll need to write the equilibrium expression, and since this molecule is formic acid, you can find that in a table. It turns out that the K sub A for formic acid, this molecule, is 1.8 times 10 to the power of negative 4. And the expression, the equilibrium expression, looks like this. H3O plus times CHO2 minus divided by the concentration of formic acid. And remember what we're looking for. We're actually looking for this expression, most importantly, because using this expression, just like what we did in question number 1, we can find the pH. pH is equal to negative log of the concentration H3O+. So once we find this, we're good to go. I'll substitute the value 1.8 times 10 to the power of negative 4 into here, and I'll substitute all of these expressions where they belong. Normally, if you were to solve this honestly, you might end up with a quadratic equation, and it might take a while to come up with the value of x. However, because this number is really small, we can assume that by getting rid of this plus x and this minus x, our answer will still be correct. Of course, I haven't removed minus x here because that's not being added or subtracted to anything. You can only do this when x is being added or subtracted. As you can see at this point, we're left with these two factors at the top and the bottom. I'll multiply both sides by 0.200. That cancels that out. And subsequently divide both sides by 0.100. That cancels this out. And we're left with negative x on the right side. So we have 0.2 times 1.8 times 10 to the power of negative 4 divided by the number at the bottom. And of course, don't forget to divide both sides by this negative 1. That will cancel out the negative, making this number negative 3.6 times 10 to the power of negative 4. And this is correct to the correct number of significant figures. Remember, this has 2 significant figures. This one had 3, so we end off with 2. We'll substitute this value into here because what we just found was x. So I'll substitute that value right here, and it becomes positive 3.6 times 10 raised to the power of negative 4. I now have everything I need to find the pH. Using this formula, I'll substitute this value right into there. So I have negative log of the number 3.6 times 10 to the power of negative 4. And that gives us a pH of 3.44. pH is equal to 3.44. We stop writing after the second 4 because this number had 2 significant figures, and you stop writing after 2 digits following the decimal place. And there you have it. Our second example on how to calculate the pH of a buffer solution.